So in my previous video, I introduced ordinary differential equations, and I gave an example differential equation. This one, as well as some others, but I showed the solution to this one. A solution to this one is the exponential of negative x. And I also showed that any constant multiple, and also explained that any constant multiple times this function is also a solution to the differential equation. One thing we can see if we rearrange this equation is that it can be written like this. So we see that what this equation really is saying is that the derivative is equal to the negative of the function. And we know that's the case for the exponential of the negative of the independent variable. If we had if instead we had dy dx minus y equals 0, then we could actually write that as dy dx equals y. And now we just need to find a function for which the derivative is equal to the function itself. And of course, the exponential function has that property. Indeed, any constant multiple times this exponential function also has the same property. So we could put a constant in front. Maybe we'll call k this time. K is any constant. Because if we differentiate this, we'll also get k e to the power x. So that satisfies this differential equation. Similarly, if we had dy dx equals 3 times y, then we need to find a function for which the derivative is 3 times the function itself. And e to the power 3x works. That solves the equation. And again, any constant multiple times this function also is a solution. Put a c. I might put a c in front. That can be the constant. So these differential equations here are very simple. They're all the form dy dx equals lambda times y. And so they have a solution e to the power lambda x. And the general solution, of course, is just a constant times that. But not all differential equations are so simple. We have a more complicated differential equation. Like say dy dx, take xy equals 0. How do we solve it? Well, this equation can be rewritten as dy dx equals xy. Now any differential equation for which we have dy dx equals some function of x times some function of y, and the functions can just be the variable themselves, or they could be a more complicated function, like say x squared, in which case this would be the equivalent equation would be dy dx take x squared y equals 0. So for a function like this, or for a differential equation, rather like this, we have a function of x, namely x squared, the function of y, which is in this case y itself, equals to the derivative of y with respect to x. Now, this is a special type of equation called a separable differential equation. And it's called separable because we can separate the y, the function of y, from the function of x. So we can just divide through by y. So we'll end up with 1 over y dy dx equals x squared. And that is convenient because now we can integrate both sides. So there's with respect to x. We can integrate both sides with respect to x like this. The integral 1 over y dy dx with respect to x equals the integral of x squared with respect to x. So we integrate both sides with respect to x. Now, the mathematicians might not necessarily like me crossing out these, but we can actually just take the integral of 1 over y with respect to y if we have this, because effectively, although it's probably not precise to cancel out the dx's, it will work nonetheless. So we got log of the absolute value of y equals, now an antiderivative of x squared is x cubed over 3, and we need to add an integrating constant, so we'll call it c. So we had that log the absolute value of y equals x cubed over 3 plus c. To find y, we just rearrange. So the absolute value of y, if we take the exponential of both sides, we get the absolute value of y equals exponential of x cubed over 3 plus our constant c. So the absolute value of y equals e to the power x cubed over 3 plus c. And now we can rewrite this exponential as e to the power x cubed over 3 times e to the power c. Now this e to the power c is itself just a constant. An exponential of some constant is a constant itself. So we can call this constant k, for example. So now we've got the absolute value of y equals k times the exponential of x cubed over 3. Now, to remove this absolute value of y, we need to take into account both positive y and negative y. So if it's to account for that, we can just write plus or minus k e to the power x cubed over 3. But plus or minus k is itself some constant k, so we can just rewrite that as some other constant a to the power e x cubed over 3. I'll do another example. dy dx equals xy. Now again, we divide through by y to separate the functions of x and y. 1 over y dy dx equals x. And again, we can integrate both sides with respect to x. And which gives log of the absolute value of y equals x squared over 2 plus some integrating constant, which I'll again call c. And then again, the absolute value of y will equal the exponential, taking the exponential of both sides. Again, we have the absolute value of y equals the exponential of x squared over 2 plus c, which again equals exponential of x squared over 2 times the exponential of c. And again, this is just a constant, which I can again call k. So again, y, absolute value of y equals k times e to x squared. Divided by 2. And then we can just write y equals plus or minus k equals e to the x squared over 2. But we really don't need the plus or minus now, because plus or minus k is itself some constant k. K can be any constant anyway, so we might just keep the same constant, or I'll change it to a e to the x squared over 2. Now we can solve more complicated differential equations of this form. dy dx equals some function of x times some function of y. For example, I'll do a more complicated example now. So how about x times the exponential function of x times y. Well, again, we have to divide through by y to separate the x function with the function of y. We can integrate again with respect to x. Integrating the left-hand side again gives log the absolute value of y. The right-hand side can be integrated by parts. So this would look like x, e, x, take. So I've taken an antiderivative of this term here in this case. In this case, an antiderivative of e to the power x is just e to the x itself. That works, so that's what I'll use. And a derivative of the first term x is just 1, so we don't need to we could put a 1 here, but we don't need to do that. And so this just gives x e to the power x take the integral of e to the power x. Well, an antiderivative is just e to the x, but we need to put an integrating constant. So I'll rewrite this again. Just log absolute value of y equals x times e to the power x take e to the x plus c. And so that implies that if we take the exponential of both sides again, we'll end up getting an exponential of some exponential functions. So we get e to the power x, e, x, take e, x, plus c. Again, this constant c, it can be factored out as just e to the power c. So we have absolute value of y equals e to the power c times e to the x, e to the x, take e to the x. And we'll just call this constant k again. So we've got k e to the x, e to the x, take e to the x. Again, we can remove the absolute value sign. So we'll be plus or minus this, which I'll just write a e x, e to the x, take e to the x. We should check that this actually solves the original differential equation. The original differential equation was dy dx equals x e to the power x times y. Very written here. Dy dx equals x e to the x times y. Check this equation here. Solve this differential equation here. This function here needs to involve this differential equation here. So we can check that by taking the derivative of this. So the derivative of this will be dy dx equals it's an exponential function, so it will just be itself times the derivative of the exponent, which is going to be x times e to the x plus e to the x, take e to the x. Yeah. Now these two. So this the derivative is just the derivative of this original function is just itself times the derivative of the exponent here, which is this function here. Now this term and this term cancel out, so we're just left with this function here, which is the original function, y, times x times e to the power x, x e to the power x, which if we look back to our original differential equation, it's just x times e to the power x times y, so they're the same. So dy dx equals x e to the power x y, which solves this differential equation. So we can see that this y is indeed a solution to the differential equation. I'll do one final example. We've already seen how this technique enables solving differential equations with the form dy dx equals some function of x times some function of y. Now, for previous examples, the function of y has been y itself, but we can also consider cases where that's not the case. For example, dy dx equals sine x times y squared. So our function here of x is sine of x, and our function here of y is y squared. Now again, we divide by the function of y, which in this case is y squared. So we get 1 over y squared dy dx equals sine of x. And then we can integrate with respect to x. Both sides of the equation. So the integral of this with respect to x, or we take, we get 1 over y squared dy, and then we take the integral with respect to y, of this function of y. So we've separated, we've got y on this side and x on this side. Now we just find antiderivatives. And we get an integrating constant again, which I've called C. So all we have to do now is to rearrange for y. So that will give us y equals 1 over cos of x minus c. And if we don't like having a negative sign in front of the constant, we can just replace it with the negative of another constant, which is the negative of that constant. So we could write y equals cos of x plus b, where b equals minus c. And now it's a good idea to again check this function to see if it indeed solves the differential equation. Now the differential equation was dy dx equals sine of x times y squared. So to find out if it solves the differential equation, we take the derivative of this function with respect to x to find dy dx for this y. And that will give us negative 1 over the square of this denominator times the derivative of the denominator, which will be negative sine of x. So the two negatives will cancel, and we're just left with sine of x over cos of x plus b all squared. But we can see that this derivative is just the square of this function times sine of x. So we can write that out. This derivative dy dx, it equals the square of y. Or I might write it out this way. It equals 1 over cos of x plus b all squared times sine of x. Now we can see that this here, 1 over cos x plus b, is y. And so the derivative is that expression squared times sine of x. But our differential equation originally was indeed sine of x times y squared, which is what we have down here. So this solution y, its derivative, equals y squared times sine x, or sine x times y, which was in accordance with our differential equation. Dy dx equals sine of x y squared. So this solution here, y equals 1 over cos of x plus b, where b is some constant, is the solution. It is the solution for this differential equation. So that's the last example for this section. In the next video, I'll go on to talk about linear differential equations that also have, so we won't be looking at ones with y squared, for example, like this case. We're looking at cases we have dy dx. We'll be still looking at first order equations, but ones of the form dy dx plus some function of x, which could be constant or could be not, times y equals some function of x. And if g of x is 0, then that will be the homogeneous case, in which case it can actually be written out as dy dx equals negative f of x times y. When g of x equals 0, this equation here can be written out like this, which you can see is just some function of x times some function of y, which in this case it is actually the function of y is just y itself. But this means that the techniques that we've learned in this video will be applicable to solving the homogeneous case of this equation here. Thank you.